Uh, I laugh quite a bit. Anyway, today we're gonna, and this is the recording here. Today we're gonna take a look at some more advanced MPLS core concepts. So as I mentioned to some of you guys who are in here, and those of you who may have walked in just now missed it, um, we're looking at some of the more advanced stuff in MPLS. So a few weeks back, we covered L3 VPN. Donald did it, and then I covered L2 VPN, which is nice, but that's the services part of MPLS. So MPLS configuration, you can, in design, you can kind of split up into two parts. So you've got the service that's actually running over the MPLS, so your VPN services or whatever the case may be, and then you have the actual core of MPLS, that core that you need to configure to actually do your label switching. That you can separate in the configuration because it's independent of any service that you might run over it. It's kind of like how you're probably not designing the core of your network based on the fact that there's HTTP running over it or something, right? Your MPLS core design is independent of whatever service you're running over it. And so today I wanted to go ahead and walk back to MPLS, take a break from the automation stuff for now, and take a look at how we can optimize the MPLS core from a service provider perspective there, because it's what I had off the top of my mind there, to be honest with you. So I didn't get time to set up this lab, as I mentioned. So right now I've got the core configured to run the label distribution protocol. We go ahead and look at the topology here. What we can see is this is the topology I've got set up right now. I don't have my drawing tablet ready or anything, so I won't be able to draw, but there's the topology. We have an interconnected core here. We've got two PEs, and then we've got 4 customer edges here. So these top 2 CEs are going to be running L3 VPN, and then these bottom 2 CEs are going to be running on L2 VPN, just to prove that the core configuration is going to be service independent, and it's going to be a nice recap of what we did from a few weeks back. So if I go back to my desktop here, if I do a show MPLS forwarding table, this is how I'm going to verify that everything's up. I can see my labels in there. So this is going to be proof that the base configuration that I did, which was set up OSPF as my IGP and set up the LDP, the label distribution protocol, to run on top of that. That's going to be proof that that part of the configuration works there. So from there, the next thing is I'm going to go ahead and set up the services. So before we go ahead and get into anything too advanced with MPLS that we're going to be covering today, I'm going to go ahead and get the L3 and the L2 VPN set up there. So for the L3 VPN, that's just going to be standard, BGP, VPN, v4, and all of that. For the L2 VPN, I'm going to be running VPWS, which is the virtual private wire service. That's that point-to-point connection that I talked about a few weeks back, and we're going to be using a cross-connect to accomplish that. So that's what we're going to go ahead and do real quick. So first thing I want to do is I'll go ahead and IP address my my CEs here. So we're going to go for IP address 10.21.31.31. And I'm going to go ahead and do a test ping out here just to make sure that that works, and it does. So I'm going to put an IP address here. Now, what I'm going to do is I'm just going to use BGP as my BECE protocol just to make things simple there. Instead of having to redistribute from BGP and IGP and have to deal with all that mess, I'm just going to run BGP natively between my PEs and my CEs. So that's that. And then I'm going to go ahead and activate the IPv4 address family and then activate the VPN v4 address family there. And I'm going to do a no BGP default IPv4 unicast. That's just a convenience thing because we don't have to run IPv4 between the PEs. We have to run VPN v4. This is going to keep the PE sessions from automatically being activated within the IPv4 address family there. So the next thing I'm going to do is I'm going to do comparing between the CE and the PE first, just so we can do the route exchange. And so we're going to do that by going into the IPv4, the configuration for IPv4, but we're going to do it for VRF. So just as a background here, if we do a show VRF, there's a customer VRF here that has the customer interface that's part of it. Do show IP route VRF customer is going to verify that that customer has its own separate routing table and all of that, as a VRF would. So what I'm going to do is I'm going to go into address family IPv4 VRF customer. That's going to launch be into a separate address family instance just for that VRF there. And then we're going to go ahead and configure our neighbor statement here. And so our neighbor on CE1 is going to be 10.21.31.31. Remote AS is going to be I'll call some eBGP connections. So I'll call it 100. And then 10.21.31.31. That should be all we need there, because we don't need eBGP multi-hop. But what I will say, preempt play here, is we're going to say AS override. I'll cover what that does in a moment. That's one of the good things I want to talk about here. So what we're going to do is we're going to go ahead and I'm just going to make a loopback interface here, just so we have a network to route over the Elder VPN. So I'm going to configure BGP there, router ID 31.31.31.31. Going to open this up this address family, and then we're going to configure the neighbor there. So we don't have to do any VRF configuration because the VRF config is just on the provider edge. I'm going to do that. And then that's it. So all I have to do here is go ahead and pump the network into BGP. If I do a try for BGP, that's in a table there. And in theory, so we can see here the BGP adjacency came up. If I go ahead and do a verification on the BE, first there's a syslog saying that the neighbor came up under the VRF customer. So if I do a show BGP VPN before unicast here, all, you can see that we've learned this network from the customer. So that's one half of the equation. So now we have to go ahead and focus on the other half of the equation, which is going to be peering on PE1 anyway, which is going to be peering over to PE2. So firstly, let's go ahead and verify that we can reach PE2. So I'm going to ping this loopback, source loopback 0, and we can see that we can ping it. And actually, just for fun, I'm going to show you that we can, the way that we're reaching this loopback is we're going to reach it over our MPLS. So you can see here we're labeling everything down to that PE there, and we're doing some load balancing there, some equal cost multipath. So what we're going to do is we're going to go ahead and define the neighbor out here. So we're going to define 22.22.22.22 remote AS 1000. We're going to define the update source to be loopback 0 there, and then what we're going to do is we're going to go into our VPN before address family, and we're going to activate this. So that's that. So what we're going to do now is going to be focused on the PE2 side there. We're going to configure the same BGP process of 1000, since we're running iBGP between the provider edges. We're going to configure our provider edge 2 here with the same thing that I had back here. So if I do a show run SBGP, just see the config we had back here. We can see that we defined the router ID and we said no HB IPv4 unicaster, so I'm going to replicate that on PE2. I'm just going to do this manually. No BGP default IPv4 unicast. And then we are going to specify the IPv4 address family for the VRF customer. We are going to specify 22.32.32, which is a neighbor there. And then we're going to do an AS override. And again, I'll show you what that does in a moment. And then we're going to define VPN v4. So I'm going to do peering between the PEs first on this side. Run AS 1000, and then we're going to define the update source. And then we're going to go over to VPN v4. We're going to activate this neighbor under the VPN v4 address family, so it forms a VPN v4 peering. And in a moment, we should see SSLog come up, but while we're waiting for that, I'm going to go back over here and define a couple of things. So we are going to define IP address 10.22.32.32. 10.22.32.22. I'm just going to ping and verify that connection's up there. Does hurt to check your work. And what I'm going to do here is make a new loopback 32.0.0.1. Whoops, not loopback 0, loopback 1. 32.0.0.1. And then we're going to advertise this straight into BGP. 32.32.32, neighbor 10.22.32.22, remote AS 100, 1000 rather. and then that's it. So now we just have to advertise the network over to it. And we go ahead and look on this. We can see here we have a PE connection up, and then we have our customer VRF connection up. So if I go ahead and do a show BGP VPN v4 unicast all, we can see here that let's see, show IPBGP. Whoops. Let's see. Okay, so we've got that up. There we go. All right, that's what I was expecting. So we can see here that on the PE, so we go ahead and do a show BGP VPN v4 unicast all. We can see that for the VRF customer, which has the route distinguisher of 1001, we've got these routes learned. We go ahead and inspect these routes in greater detail. We can see here we've got the MPLS labels there. We've got the extended community, the route target here, which is going to allow us to import it into VRF there. It's basically exactly what Donald showed you from that demo there, but just to prove that we have the service up, what we can do is we can look in our routing table on the CEs. That's routed there, so if we ping from source loopback 1, we can see that we have connection between the CEs now over the Elder VPN. So that's the Elder VPN. If we go ahead and look at the L2 VPN side of things, just to get that particular service up, I'm going to go for a cross connect there. So it's going to be using the older cross connect style because I can't be asked to manually set up the pseudo wire. So that's going to be on the customer facing interface. We're going to run cross connect to the other PE. And the VCID, we'll call it 2122. And then the encapsulation is going to be MPLS there. No, that's fine. Whoops. Int G4X connect. We'll go ahead and paste this all in. Yep, that's fine. Alrighty. And then as far as the configuration on here goes, it's going to be the nearly the exact same thing. 2122 for the virtual circuit ID that has to match, and then we're going to go for MPLS. And in theory, we have a targeted LDP neighbor, we have a pseudo wire that comes up, and unless I boomer something, that should mean that we can ping over from our CEs. So it's as simple as the L2 VPN configuration gets there. Not much I have to worry about on that front. So if I want, I can just run EIGRP over it. There, EIGRP 100, network 0000. And in theory, we have our EIGRP neighborship that's forming over the core there. If I go ahead and put IP addresses on the loopback interfaces, we can see, because I put the global network statement, that we have the loopback that's reachable there. So that works. So we've got Elder VPN and L2 VPN set up right now. So that's the services. Now I do want to go ahead and cover one thing that I did there, and that's going to be this AS override. So I don't know if Donald showed you the AS override or whether he did allow AS in, which is the other way you could get around this. So basically the idea is that because you're routing over the provider, if these guys have the same BGP AS number, the way that BGP does its loop prevention is that it looks in the AS path to see whether its own AS number is there. And so if we didn't do this AS override, what would happen is, because this is an eBGP connection between PE and CE, the CE is going to go ahead and put its own AS number when it exports the route to the PE, which is going to be AS number 100. It's going to go over the VPN, and then it's going to get to the other CE, and the other CE is going to drop it because both of the CEs have the same AS number, and that AS number is going to be in the AS path by the time that route gets to the other CE. And so from there, you're going to get a loop prevention drop. So AS override basically says, override the AS number that came in with my own AS number. So we do a show BGP VPN v4 unicast there on P2. You can see here that the AS path is going to have 100. Should have 1,000. Let's look. We go ahead and go look at the CE. Show BGP. Yep. So that's the AS override working there. Check on our own router. So the AS override is going to go ahead and override the path here to 1,000, so it doesn't trigger any loop prevention stuff from seeing its own AS number there. So that's what that command does. So that's the services configuration done. Now we can take a look closer at the core. So a couple things to know about the core here. Firstly, the way that this works is that we take a look at the L3 VPN side of it. When we have a VPN traffic coming in, it's going to hit the PE as an IP packet, and then it's going to go ahead and do a lookup there in BGP, and it's going to go ahead and see that the next hop is going to be the remote PE. And so that's the actual LDP label that gets put on top of it. There is a VPN label. If I do a show BGP VPN before unicast all labels, we can see that there is a VPN label that goes on top of that, the outbound label of 22,013, and that's generated and advertised by the remote PE. So that's the underlying label. There's a 2-label stack for LDP-VPN. And then on top of that, we've got the transport label that moves it to the next hop, which is going to be PE2, judging by this next hop here. And so that's what the actual MPLS core is doing, is switching on. So we can see here that the outbound label for 22 is going to be 22,013. And then if we look at the MPLS forwarding table, we can see that the outbound label for PE2 is going to be either 11,010 or 13,010. And that comes from the MPLS forwarding table on these provider routers here. So 13,010 or 11,010. So that's how the switching process works. Now, the problem is that this requires that our entire path is label switched, right? So if we go ahead and do a trace route to that 32,001 network, we source from our loopback 1 here. That requires our entire path is label switched here, right? So we first hit the first PE, and then when we hit the P router, we have this label stack. When we hit the other P router, the P4 here, we're going to have a different label, and then we're going to switch it down. But if any one of these interfaces has their LDP relationship die, what's going to happen is that what's it called? That interface is going to be no longer capable of supporting the MPLS packets, and so you're going to get a drop. So the golden rule of MPLS here is that every router and every link in the path has to be able to support it. Well, what if, right? What if you have an LDP drop, right? Because IGP and LDP run independently of each other. LDP will piggyback off of the IGP, but IGP doesn't necessarily know if LDP goes down. So if the LDP neighborship goes down, OSPF doesn't necessarily know that. And so the result is that you could continue pushing that traffic down the unlabeled path and get a broken LSP is what we call it. So you would be dropping your traffic because the IGP is trying to force all that traffic down a path that doesn't support MPLS because you had a link where your LDP neighborship died. And so that's where the concept of LDP-IGP synchronization comes in. This is one of the first advanced core features that we're going to take a look at there, where what we're essentially doing is we are intertwining the operations of LDP in the IGP. So basically what we're saying is if LDP dies, so if the protocol that's actually pushing out our MPLS labels dies, then we're going to go ahead and link those two states together so that effectively one dying causes the other to recalculate its path. So the way that we can do this here is if we go ahead and take a look at our IGP configuration. If we go ahead and do MPLS LDP, we can see that there's a sync command here. And that's going to be our configuration, just that sync command. In iOS XR, if you guys care, it's going to be LDP-IGP sync. But in iOS, it's going to be just standard MPLS LDP sync. I'm just going to go ahead and run that on all of these guys real quick. And that's pretty much the only configuration that goes into synchronization. Router OSPF1 and VE. And so we've got synchronization enabled now. So if I go ahead and do an MPLS, LDP, IGP sync, we can see that we have LDP configured, we have the LDP-IGP synchronization enabled, and we have achieved the sync status that appears reachable, right? So this is the command that we use to verify LDP-IGP synchronization. Now, if you notice, if we look at our MPLS forwarding table here, to get to PE2, we have two paths here. So we can go through this path up here, PE1, PE1, P2, P2, or we can go down list path, right? PE1, P3, P4, P2. So we have two different paths from the perspective of PE1, where we could technically take our traffic. And so that means that if, say, list link dies here because our LDP relationship dies, but our IGP still stays up for whatever reason, we can force the traffic down here, which OSPF would not natively do on its own, because from the IGP perspective, from OSPF's perspective, this top path is still entirely up. So it's not going to ever want to switch down unless LDP forces it to. So that's what we're going to do. If I go ahead and go back here, what we're going to do is we're going to put a little trick on it. So LDP uses port 636 there. 646 rather, I'm sorry. So if we go ahead and take a look at our access list, we're going to play a little CCNA trick on it. We're going to use an extended access list. We're going to call this block LDP. And then what we're going to do is we're going to deny TCP any 646 any EQ 646 any 20 deny TCP any EQ 646, and then I'm just to cover all my bases there, just gonna fully nuke out LDP there, and then we're gonna do any. So if I go ahead and look at my access list, we can see that we have an extended ACL called block LDP, and that's going to be that. Now, what I'm going to do is I'm going to go ahead and apply it to the interface facing P1 there. So the interface facing P1 on the PE is going to be G1, and I'm going to apply this access list, IP access class, IP access group rather, block LDP, and we're going to do for inbound packets. That way, any of the LDP keep alives that are coming in from the first provider router here is going to get dropped because of the ACL. So if I do a IP access group, IP access list, we can see that we've got a couple of matches there. And we can see that the LDP neighbors went down because the hold timer is expired. So basically, we missed enough hellos on this end of the relationship that we couldn't keep the LDP neighborship down, or keep the LDP neighborship up, should I say. So if we go ahead and look at our LDP-IGP sync now, we can go ahead and say that the sync status, the synchronization is not achieved, but the peer is still reachable. So what this is saying is that we can still reach the peer because we have an IGP connection. So we go ahead and just ping the loopback here. Source loopback 0. We can still ping it. It's just that we don't have an MPLS neighborship up there anymore. And so the IGP synchronization is recognizing that and saying that, okay, well, you don't have synchronization. You don't have harmony between your LDP and your IGP anymore. So what this does, it's kind of sneaky. What this does, it is going to bump this metric up to the max. So that's what LDP-IGP synchronization achieves. It takes the link where your LDP relationship went down, and it's going to bump the metric to 65,535. So ordinarily, OSPF's got to look at the cost, and it's going to say, okay, well, I have no reason to not use this path. Now it has a definite reason, because we've bumped this metric up on the transit link between PE1 and PE1 up all the way to the max. And so OSPF is going to effectively ignore this link. If I do a show IP route, or show MPLS forwarding, so if I do a show IP route, now as opposed to having two paths to 22, 22, 22, 22, we just have 1. And therefore, if I go ahead and look here, now we can basically guarantee that our traffic is still going to flow, because instead of having to play a game of dice effectively on whether it's going to take the broken path or the working MPLS path, now we can guarantee it's going to take the working labeled path, because the IGP has effectively completely eliminated the path to P1 as a possibility. So if I do, before I turn it off, I'm just going to do a verification command one last time. We can see a sync is not achieved there. If I go ahead and remove the access group on the interface there, in on that. So in a moment, we should have our LDP neighbor coming back up, and now we can see that the sync is now achieved again. And if I do a show IP route, now we have our load balanced ECMP path back. If I do a show IP OSPF database router, we can see that the metric is back to normal as opposed to the 65,535 metric, the max for that 16-bit value there, that the metric is. So we've reset it back from the maximum to what it's supposed to be, and now we're doing our ECMP. And now if we go ahead and do a trace route, we're still taking the 13 path, but theoretically now at least have the possibility to take the path through V1. So that's that. That's the LDP-IGP synchronization functionality. Now, there's some other protection functionalities we can go ahead and take a look at before I, because the 2 things I want to overview here, really the 5 things, are going to be synchronization, which I've done already, session protection, which is going to be next, and then we're going to take a look at MPLS traffic engineering, MPLS Explicit-Null, and then we'll go ahead and take a look at the bleeding edge for MPLS, just as a kind of a wrap up there, which is going to be the segment routing. So what I'm going to do is we have synchronization enabled, and we have things back up, is we're going to go ahead and take a look at a feature called session protection. And synchronization and session protection kind of go hand in hand there. They both relate to answering the question of what happens when an LDP neighborship goes down. So when you have a directly connected LDP neighborship, because if you're not familiar with how the LDP neighborship process works, you basically multicast out to the all routers address there, and LDP hello through UDP, and then you that gets flooded out to the local segment, and then you do your unicast TCP from there. Well, there is a form of LDP, and you've already seen it actually. I configured it earlier. It's called targeted LDP. So we go ahead and take a look at our LDP neighbors. Here we can see that we have appearing an LDP peer that goes to 22, 22, 22, 22. You might ask, well, how is this the case, right? Because you said that the UDP hello is just flooded out to the local segment. How are we forming a multi-hop LDP session? That's what it effectively is. Well, you can see here that if we look at under the LDP discovery sources, this is saying that, okay, well, I flooded my UDP multicast out of Gig Ethernet 2 using the source address, and I picked up another neighbor. But we have another way we can do it. It's called a targeted hello. And a targeted hello is basically going to take that UDP multicast that was for the hello and flood it out as a UDP unicast. And so that way we can do our multi-hop discovery there. There's a lot of uses for this. You have L2VPN, which uses it. And then you have session protection, which uses it. With session protection, what you're saying is when the neighborship goes down, when the LDP neighborship goes down, we're going to take this and we're going to use a targeted hello. So if there's another path that we could possibly get to that neighbor with, we're going to form a targeted hello with the neighbor that just went down. And what we're doing there is we're protecting the label entries that they've already advertised. So the idea is that if you have a lot of flapping links, let's say, so you have a link that's constantly going up, constantly going down, and the LDP neighborship is going up and down with it, the idea is that you don't want things to be too volatile because you're constantly relearning the labels there. And you have a lot of labels that can cause a lot of control plane overhead. And so part of the discussion there is going to be how do we protect the labels we already learned and keep the router from forgetting about them. And that's going to be session protection. So we go ahead and look at the session protection configuration here. It's going to be pretty simple, just like the synchronization configuration. It's mainly the theory behind it and why we use it that's complicated there. But it's just going to be, I have to actually look at this, MPLS-LDP Session Protection. And so that's the global configuration there. We can do a duration there to how long we want to sustain that session protection for. So if it's, we can specify duration that way. If the neighbor's down for too long, we can end up dropping it anyway, since this is designed to protect against flapping links and volatile situations rather than just neighbors dropping there. So we can specify a duration that we're going to protect the session for, and we can specify an access list that specifies the actual peers that we want to do protection for, just in case, there's a peer that we don't really care about that if it goes up and down, but we can protect this specific group of peers. So that's going to be session protection there. And if I go ahead, and that's really it as far as the session protection configuration goes. So what I'm going to do is I'm going to paste on the rest of these routers here. Probably should end this. And then session protection and session protection. That's really all that goes into our session protection configuration. It's just one command like the synchronization is. So if we go ahead and take a look at this now, now if we go ahead and effectively shut down our link. So if we shut down our link from R1 to, from P1 to PE2 there, we shut down that link, there's still another way you can get, there's still a multitude of other paths that we could use to get around the P1. So the idea behind this is if we shut down this link, we should see that we have a session holdup that's initiated. So this is our session protection notification. If I do a LDP neighbor, now we can see that we have a targeted hello that's going from P1 to P1 here. And the idea is that rather than doing our discovery, we're doing our multicast discovery, we're doing a unicast hello straight to that neighbor so that we can maintain the neighborship even if it goes down, right? Now, the reason I say that this is going to go hand in hand with synchronization is because session protection does nothing about the actual path itself, right? All it's protecting is the label entry. So you're going to see that all of the labels that were learned from our from P1 here are going to be missing. We don't see anything that begins with 11, which is the label prefix that I gave P1. We don't see anything that starts with 11. But if I do in show MPLS LDP bindings, and that's going to show our label information base, we can see that we do still have the labels, right? So now if we go ahead and filter through this list, we can see, oh, here's a label. We learned this from label switching router, which is what LSR stands for, 11.11.11.11, which is P1 here. That's the router I shut down the link to. And we can see that we still learn it, right? We still kept it in our label information base. So the difference between MPLS forwarding table and this command is the difference between, say, like show IP route and show IP ceph. It's the rib versus the fib, the control plane versus the data plane. So this label information base here, right? This is in the control plane. This is like our routing table, like our routing information base. And then the show MPLS forwarding table is our data plane, what actually gets used to forward the MPLS packets. So the idea being that when we're doing our remote binding here, we are keeping the label bindings, the label advertisements from P1 in the control plane, in the routing table, but we're not actually using them to do the forwarding. And so this makes sure that we don't black hole traffic because the link between PE1 and PE1 is down. That makes sure that we don't black hole the traffic because none of the labels from PE1 are going to be in this forwarding table, but they are still being kept in the control plane such that when the link comes back up and P1 is able to form a neighborship there with LDP with PE1, we don't have to completely re-advertise all of the labels back over. We can just flip a switch and all of the labels that PE1 has advertised come out from the control plane and into the data plane table. And so that way, even if we have a volatile link, we're only advertising the labels once, right? Because the subsequent times when it comes back up and comes back down, PE1 is just going to flip a switch and say, okay, you P1 labels, you're good to come back into the data plane. You're good to be used for forwarding again because the link's back up. And if it goes down and up again, that process is going to keep repeating. So if I go ahead and go back here and I no-shut the link to P1, we can see in a moment that this is going to come up. And so the session recovery has succeeded. The interface is up, and we have an OSPF adjacency that's coming up. And if I do a show MPLS LDP neighbor, we can see that as opposed or alongside target hello, in this case, it's going to drop in a moment, but alongside target hello, we also have our normal UDP multicast discovery. And so if I look at my MPLS forwarding table, now we have our 11 labels back in there. So we didn't have to re-advertise it again. We just flipped the switch and moved it up from the forwarding table into, or moved it up from the label information base, which is the control plane table, up to the MPLS LFIB, which is going to be the label forwarding information base, it's being data plane. So that's session protection. Again, it's a simple to configure feature. It's just that one command in global configuration mode, but the theory behind it and understanding why we want to use synchronization and session protection and how they go hand in hand, that's the theory that ends up being relatively complicated anyway compared to the configuration. So that's that. Now, the one thing I didn't want to cover real quick is Explicit-Null, and then we'll move on to the last two features there, which is going to be RSVP-TE. That lets us do our traffic engineering, and then I'm going to show you the bleeding edge of MPLS if you're interested as a sort of wrap up there. So the idea behind the Explicit-Null, it's also a fairly simple feature to configure there, but the theory is what is, again, relatively complicated. The idea behind Explicit-Null is going to be primarily QoS related. So if we go ahead and take a look at our MPLS forwarding table here, we can see we have a bunch of pop labels here. It might be helpful if we go ahead and take a look at, P2, that's actually in the middle of the path. We can see that we have outgoing labels here, but we have a bunch of pop labels. Go ahead and take a look at the show MPLS LDP bindings. We can see that we have a bunch of imp nulls. This is going to stand for implicit null, and that translates to these pop labels. So we go ahead and look at the binding for the lib entry for, let's say, 13, 13, 13, 13. I think there's a way I can look for it. Yeah, 13, 13, 13, 13, 32. So we can see here that we have the label information base entry, and the remote binding for LSR 13, 13, 13, 13, which is going to be directly connected to. P2 is connected to P3 over this link here. We're going to see that the label there is going to be implicit null. This is a reserved label. It's label value 3. And the idea behind implicit null is that you're going to pop the label before you go off, and it's going to keep double lookup from happening. So assuming you have an L3 VPN, you have a double label stack there. You have a label that's for your LDP, that's your transport, goes from PE to PE, and then you have your VPN label that actually tells the endpoint PEs where the network is and what VRF it's in. So that double label stack is what we're concerned about, because the idea is if we don't have this implicit null, if we forward the double label stack as is to the ultimate router, it's going to be the last router in the path there, that last router has to do a double lookup, because it has to look up the first label, the top label, the LDP label, to figure out that, hey, this is going to be for me, right? It has to figure that out, and then it has to figure out a second time, it has to do a second label lookup to figure out what the VPN traffic actually goes to. So the idea behind the feature called Penultimate Hot Popping, which is PHP, which is this null here, not the shitty web language. Penultimate Hot Popping. The idea behind that is that we are doing a pop off the top label. We're removing it, and we're only sending the VPN label to the last router, so that the last router doesn't have to bother itself with a double lookup to figure out that hey, this traffic is for me, it can just go straight to VPN label lookup. It can go for that. So that's the idea behind penultimate hot popping. But the problem is that if you're doing QoS, where you're using the top label to carry a QoS tag in the MPLS, either traffic class or experimental bits, it depends on how old you are, what you call it there. If you use the MPLS traffic class or experimental bits to carry a QoS tag, if you remove that MPLS tag, all of a sudden you are now removing the QoS with it, right? Which means that your QoS stops one hop short of the end of the path, which might not be what you want. You might want the last router there to be able to use the QoS there in order to do whatever you're doing with the QoS, whether it be queuing or whatever the case may be, right? So that's the main problem, right? When we're doing QoS, we might not want the label to be popped off because as we're popping off the label, we're popping off the top QoS tag with it. And so the solution there is going to be explicit-null. So implicit-null means you're removing the tag. Explicit-null means you're swapping it with label value 0. And that's going to be your explicit-null. It's going to move on to the next router. You still have a double label stack, but the idea is that the last router in the path gets it. It sees that the label value is 0, so it ignores it. And then as it reads through the rest of the label, it's going to see the QoS tag, and then it's going to take note of that before it removes it. And so that makes it such that your QoS policy can extend end-to-end from PE to PE. So the solution for this is actually fairly simple. We're going to advertise an explicit null. So the idea is that the reason that this is going to pop the label is because the neighbor advertised, the ultimate router advertised an implicit null. So the way that we keep that from happening is we make sure that the last top router will advertise an explicit null instead of an implicit null. So the way we do this is we say MPLS-LDP explicit null, and here it says explicit null, we're going to advertise the explicit null label in place of the implicit null. So if we look at the MPLS sorting table on P4, we can see that 22, 22, 22, 22 is we're going to pop the label. We're going to see list entry change in a moment as soon as we go ahead and apply this command. You can do an access list to filter it down. So 4 would be an access list that specifies the actual specific destination prefixes where we want to advertise this explicit null. And then this 2 is going to be another access list we can use that specifies not the destination prefixes, but as the help entry says there, the LDP peers that we're going to be advertising the explicit null to. But we can just hit enter here, and that's just going to do it for all of them. That should be it. If we go ahead and do a forwarding table, now we can see that there, instead of saying pop label, it's going to say explicit null. If I do a show MPLS LDP binding for 22, 22, 22, 22, 32, we can see here that instead of an imp null that we saw earlier, we have an exp null, meaning that the label stack is going to have a 0 explicitly. We can go ahead and test this. We can go for a trace route again. And you can see now, whereas earlier we just had this VPN label, so this 22,000 is the VPN label, whereas we just had the VPN label here. Now if we do a trace route again with the explicit null stuff enabled, we have this top label here being a 0. So it moves on to PE2 with that 0 label. And the idea is that, again, if we had some sort of QoS marking on top there, we could preserve that QoS and preserve the QoS policy going from end to end. So that's the explicit null functionality. So that's synchronization, session protection, and now I have explicit null. Explicit null doesn't really have much to do with either of those prior topics, but I figured it might be something cool to show. So now we have 2 more features to look at. We have MPLS-TE, and then we have SR. So MPLS-TE is going to be where you might find use in this kind of explicit null, because the idea is you're going to be doing traffic engineering there between the PEs in order to do QoS, in order to reserve bandwidth, in order to do traffic steering. So the idea behind LDP is that it's a non-traffic engineered label switch path, meaning that from LDP's perspective, all it's doing is it's looking at the prefixes in the IP routing table, And then it's saying, okay, what's the next hop of this? Okay, now I know the next hop, we're going to go ahead and generate a label for this based on that next hop. And so it's very tied to the IGP in that sense. Whatever the IGP decides the best path is, LDP is going to inherently select that as its own path, right? So if the IGP path changes, the LDP path changes. They are tied together. And with RSVP-TE, we're saying, no, we're going to decouple that. We're going to take the IGP and we're going to put it in its own little corner. And then the RSVP-TE, which is the Resource Reservation Protocol, you might have heard that if you've done Integrated Services QoS study. The idea there is that we're going to go ahead and separate out RSVP-TE, and we're going to let RSVP-TE generate its own path that's independent of the best path that the IGP chose. And funnily enough, we're going to use the IGP in order to do a transit there for RSVP-TE. You'll see what I mean in a second. So the way that we do this, it's actually a very involved configuration, unlike the previous 3 features that we looked at. It's actually a very involved configuration there. So first thing we're going to do is within the global config, I'm going to go ahead and separate out these guys into a tab group because I don't want to type out these commands on a million different routers. Okay. Interesting. Why is this? Send to new window. Okay. If I drag this back in, does that fix the glitch? It does. Okay. So now what we're going to do is we're going to go ahead and I'm going to move all these guys into configure mode so that we can run the commands. All right, cool, you're already in configure mode. So what we're going to do is we're going to run MPLS traffic engineering tunnels from the configuration mode. And that's going to go ahead and enable our traffic engineering functionality, our tunnels. And then we have to go under all of the interfaces here and do a couple things. So firstly, we're going to go int 1 to 4. Actually, I don't want to enable it. I'll do PE separately. So we're going to go ahead and do G1 to 2, loopback 0, which are my internal facing interfaces there. And I'm going to do a couple of things. So firstly, actually, not the loopback. I'm going to go ahead and do MPLS traffic engineering tunnels. So it's the exact same command that we ran out in global configuration. It's just that Cisco makes us run it again in the interface configuration. And then, so that's going to enable the MPLS-TE functionality. And then we're going to run IP RSVP bandwidth. So this under the interface enables that interface to participate in MPLS traffic engineering. This enables that interface to participate in RSVP. So we do show MPLS forwarding or show run S interface or net or show run and G1. That's what I'm thinking of. We can see that we have MPLS traffic engineering tunnels under this interface, and then we have RSVP bandwidth there. Now, if we go ahead and take a look at the OSPF there, we can run the TE extension. So the idea is that RSVP needs the IGP's help in order to determine whether the path is valid. So it's going to use the IGP extension in order to carry entries about the reservation that we're making, about the path that we're reserving through the core, as well as to check whether that path is valid by the IGP in the first place. So even though it's independent from the IGP path, we still need to configure MPLS traffic engineering in the IGP. And for LSPF specifically, we've got 2 configuration commands we need to do. We need to do it for the area, and then we need to specify a router ID. So for the traffic engineering area, we need to specify an area number. Well, I'm running area 0 here, so that's that. Now I do traffic engineering again. We've got a bunch of commands here. Most of these are not required. The top and the bottom are though. So we need the area to enable MPLS traffic engineering in that area. And we need the router ID because MPLS traffic engineering is going to use this on the back end to do good traffic engineering. So that's that. So that's the configuration we need. So if I go ahead and go on, I'm going to go ahead and go into my text edit here. And we're going to configure all my interfaces to support MPLS traffic engineering tunnels. And then we're going to go into our interface range, and we're going to enable MPLS traffic engineering tunnels. We're going to go into IP RSVP bandwidth there to enable it. And then we are going to, it doesn't hurt to enable IP RSVP bandwidth on the loopback as well, although it won't let you enable this traffic engineering tunnels command under the loopback. Doesn't hurt to enable RSVP under it though. So if we go under RSPF1, now we can specify our MPLS traffic engineering tunnel or area 0 and MPLS traffic engineering router ID loopback 0. That looks right. Yep. And then we're going to end this. Before I do that, though, I'm going to go back on PE1. I'm just going to configure bandwidth under here just to show you that it can be done. So I'm going to go on PE1 here, and we are going to, there we go. Going to go ahead and go here. That does that. We're going to do that. And then we're going to go ahead and do G2. And yep, that should work. So what we can verify this is if we do a show IP RSVP interface, we can see that we have these interfaces enabled for RSVP, as well as that we also have interface bandwidths defined. So by default, it's going to go ahead and take up 75% of the interface bandwidth as max reservable. If you want, you can change that. It's not terribly important in this case, but because I don't really care about how much bandwidth it's reserving if I'm not reserving any bandwidth. But if you do care about that, you can manually define the bandwidth it's allowed to take via this % command, or you can specify explicitly how much kilobits per second you want RSVP to be able to reserve in the control plane maximum on that interface. So if I go ahead and do MPLS traffic engineering, that's going to be a lot of our verification there. We can look at, let's see, we can look at MPLS traffic engineering topology, and that's going to go ahead and show us that we have a bunch of entries here in the IGP for the MPLS traffic engineering. Now, MPLS traffic engineering rides on an LSA that you probably haven't heard of being used in LSPF, which is going to be the LSA type 10. So in LSPF-V2, you have 3 what we call opaque LSAs. Those are open LSAs. So whereas you have like type 1, which is a router LSA, type 2 network LSA, those have very clearly defined roles. For these next 2 features, what we're going to see is that it doesn't use any of those LSAs. It uses type 10 LSA in order to carry itself. And the type 10 LSA is going to be the opaque area LSA. Now in LSPF-V2, you have 2 more opaque you have 2 more opaque LSAs. You have an opaque link LSA, which is type 9 in LSPF-V2, and we have the opaque AS, which is going to be type 11. And what those, again, opaque means that it's open usage, and then the difference between 9, 10, and 11 is that is the scope of the LSA. One is limited to a link, one is limited to the area, and one is limited to the AS. Now, you don't really see 9 and 11 too often anymore, but you will see, depending on what you're doing, you will see opaque area. Self-originate. And we can see here that we have an opaque type 1, which is our traffic engineering, and we're advertising our MPLS-TE router ID, and we're advertising all this information about the links that we are capable of doing our traffic engineering on. So what we can do is if we go ahead and form tunnels now, we can do our traffic steering. So right now, the PE, based on its LDP label, is going to go the shortest path. So it's either going to go this way or it's going to go under here. Now, let's say that I want to have this go on a bunch of other links, right? We can have this go on PE1. You know, let's say we want to swoop down to P4 here or whatever the case may be. We can specify an explicit path saying, ignore what the IGP says the best path is. This is the path I want you to go on. So right now, let's say I want things to go from PE1 to P1 to P3 to P2 to P4 to P2. I want this to go in this convoluted topology. I'm actually going to write this down so I don't have to reference it again. So we're going to go from PE1 to P1 to P3 to P2 to P4 to PE2, and then that's that. So keep in mind that the VPN, again, independent of this, but I just want to go ahead and verify real quick that what the path is. So that's the path that's going on right now. It's going on a very short path. We're going to change that just as a proof of concept. So we're going to go ahead and generate tunnels here. Now, the thing to remember about these tunnels is that they are unidirectional, meaning that we don't have to specify them both ways. We can just specify them on one provider edge to the other provider edge, or from one router to the other router, and we don't have to specify them backwards as well. Although it's common practice too, because what's likely the case is that if you want traffic engineering to go one way, you probably want it to go back the other way as well. So it's common practice too, but it's by no means a requirement there. What we're going to do is we're going to create a tunnel interface. That's tunnel 0. And then there's a couple things that we need to do here. First thing we need to do is we need to change the mode of the tunnel to MPLS traffic engineering. That's that. And then we need to change the IP address to IPN number 350. And what that's saying is basically we're not configuring an explicit IP address on this tunnel interface, but I'm telling the tunnel interface to take on the IP address of the loopback interface here. So that's that. And then from there, what I'm going to go ahead and do is let's go ahead and review what our tunnel interface configuration is so far. So we've made the tunnel and then MPLS tunnel, and then we've specified the IP address as taking on the IP address of the loopback interface. So that's the basic configuration there. Now, before I go on, we are going to go ahead and specify the path. So the idea is that we are going to create something called an explicit route object, an ERO, that basically goes from PE to PE. So that's going to be done via this IP explicit path. We're going to name this PE1, PE2. And now, if we go ahead and look at this, we have a couple things here. So the first thing we want to do is we want to specify index, and we're going to give an index number. And then we're going to want to go ahead and specify either a next label or a next address. So this up here is going to be your exclude. You don't have to worry about that. Mainly what we're going to be looking for here is next address. So I'll do next address. And then the IP address here is going to be at the next hop. Now, it's also, you also have to concern yourself with whether the target address is loose or strict. What that means is effectively, is it directly connected, or do we have to do routing to get to it? So I'm going to use the loopback interfaces as my next hop, which means that we have to specify it as loose. If we're using the actual interface IP addresses and we're specifying it hop by hop, we can actually just enter the IP address, and that's then defaulted to strict. But if you're using loopback IP addresses as your next addresses, you have to do loose. So from here, we can enter the IP address. Now, the important thing to remember here is that you have to specify your IP addresses as though you're actually going from hop to hop. Like, you have to get into the mind of a packet and think, if I'm going from PE1 to PE2, what are all of the next hops I want to get to? Because you have to specify every single one of them in this explicit route object. So if we're starting from PE1, let's type the address of PE1. And then we want to go ahead and move to P1, right? So get into mind the packet and say, what do I want the next hop to be? Okay, well, the next hop is going to be P1, which is going to be 11.11.11.11. And then again, get into mind the packet. We want to move to the next hop, which is going to be P3. So index 30, next address, loose 13, 13, 13, 13. And then we want to move to P2, which is going to be 12, 12, 12, 12. And then we want to move to P4, which is going to be 14, 14, 14, 14. And then finally, we want to move to PE2. Next address, loose 22, 22, 22, 22. So what we're saying here is that if we're a packet going from PE1 to PE2, we want to go ahead and specify this local router first, and then we're going to specify every single hop following that where we want the packet to go. So we exit out an explicit route object. So the way you can verify it is you do a show IP explicit paths, we can see it's got to list all the paths out there. It's got to be a loose source route. So if we go ahead and do go back into our tunnel, for everything we're going to do following this is going to be under this MPLS traffic engineering tunnels. Or I'm sorry, tunnel MPLS traffic engineering. Whoops. So everything we're doing here following the tunnel mode and the IP unnumbered, it's going to be all under here. So the first thing we want to do is we're going to do auto route announce. What that does is it's going to go ahead and announce the route through the IGP. So it's going to use that type 10 LSA to advertise the route that the tunnel is following. From there, we can do a couple things. We can specify the name of the tunnel. So let's say this is PE1, PE2. And then tunnel MPLS traffic engineering. The next thing we want to do is we can specify bandwidth reservations if we want, and it's going to be using RSVP to do the bandwidth reservation, the control plane. We can specify binding sits for segment routing and all of that. We can do the LSP directionality. This has got default to unidirectional. We can change that if we want. We can set the experimental values and all of that. And then finally, what we're going to do is we're going to enable path option. And we can set a preference there. So it's going to be the lower number has a higher preference. And then what we're going to do is we're going to go ahead and do a explicit route name. And then we are going to specify an explicit path. So in that case, we're going to do our PE1, PE2 explicit route object. So if I do my tunnel interface now, we can see there's that configuration there. And in theory, this should come up. Path not valid, no destination. Oh, right, I forgot to do something. Tunnel destination, we have to specify the destination of the other PE. Oops. Let's look. MPLS traffic engineering tunnels. So here's our verification command. And in theory, this should come up soon enough. Let me go ahead and do something real quick. Whoops, did not mean to do that. So what we can do is we can go ahead and tunnel specific, tunnel set. What we can do, let's see. Okay, show run interface tunnel 0. IP-RSVP interface. Let's try something. Let's do verbatim. I've seen bugs here with, let's do verbatim. Let's see what just comes up with that. Okay. Okay, so this comes up now. Now we're doing verbatim. So the idea with verbatim, here, is that we're going to be bypassing the verification check. I have seen with ISIS that without this verbatim, for whatever reason, the IGP extension here is bugged in this code and doesn't like to check. So what verbatim says is basically we're going to bypass the IGP extension check to see if it's a valid path. I know it is. And we're just going to go ahead and bring up the tunnel interface based on that. So not an ideal command, but time is limited. So if we go ahead and do our verification here, we can see that we have a valid path. The signaling is connected. It's a verbatim path that's explicit. And so here's our verification command and all of that. So now, if we go ahead and do a trace route from this end, we can see that as opposed to this sensible path that we had earlier, we're now going through a stupid path. So we have, we're starting from provider edge 1, and then we're going down to P1, we're going down to P3, P2, P4, and then PE2, and then CE2. So this is in line with the explicit path object I had here, where we had 21, 11, 13, 12, 14, and 22. So this is exactly what I specified in the explicit path, and so RSVP is reserving the path for it. Now, how this works under the hood, if we go ahead and take a look at the tunnel interface here, we have a new tag here. It's got to be bracket T, and that means it's got to be forwarding through our LSP tunnel. So we go ahead and do a detail option here. We can see if we go down here, actually it's not too important. The main thing that's important to realize is that we have a label here. So we look at 11,011, and we look for that on PE1, show MPLS forwarding table. We can see that we have 11,001, and this is going to be our TE tunnel label, and then it's got to switch it down to 13,011, 12,011, 14,011. So RSVP is effectively taking LDP's role here, and they're entirely separate, so you don't have to have LDP running for RSVP to work. The idea is that RSVP is going to generate its own labels, and then because these are RSVP labels, they're going to be preferred to your LDP labels because RSVP implies traffic engineering. So in that sense, you're going to have this up and working here with your RSVP labels, and this is going to be what drives the path down. Okay. Now, the thing to note here is that these are, again, unidirectional tunnels. So just because PE1 has a tunnel with PE2 does not mean it's the same thing the other way around. So if we do a trace route from CE2 to CE1 instead of CE1 to CE2, we can see that we're still going the regular path. We're not going the traffic engineered path. The traffic engineered path is only for traffic that PE1 is pushing into MPLS. So it's not, again, it's not a bidirectional tunnel, it's a unidirectional tunnel here. All right. So that's MPLS traffic engineering. There's a lot more you can do with it, but this is just kind of a sneak peek at what it is and how we can use it to do our path engineering. The next thing we're going to do in the last thing is going to be the bleeding edge of MPLS. So the idea of MPLS is that LDP is just another control plane protocol that we have to run. So we have IGP running, and assuming that we're doing traffic engineering or whatever, we have either LDP or RSVP, or in this case, even both running. So right now we're running IGP, LDP, and RSVP. So you can think about how in a large-scale environment, that might become cumbersome, right? Because you're running 3 protocols to maintain your MPLS core. So segment routing proposes that we take all of that and we push it into one. We use our IGP to do our MPLS signaling. And so that's what we're going to go ahead and configure. So we're going to rip out MPLS LDP. We're going to rip out RSVP. And then we're just going to configure segment routing, which is just going to run over the IGP. It's got to use the exact same thing as what TE used, which was the type 10 LSA, in order to communicate their labels practically, but these are going to be called segments in place of labels. So what we're going to do is we're going to go ahead and remove our traffic engineering tunnel, and that's going to bring that down. What we're going to do is we're going to go into config T, we're going to run OSPF1, and then we're going to no MPLS LDP auto config and no MPLS traffic engineering area 0. And I'm going to go ahead and remove session protection. No MPLS session protection. Or no MPLS LDP session protection. All right. So that's all of our LDP stuff down. So we look at our forwarding table. It's not empty yet, but we have a bunch of no label entries here, meaning that it's effectively like we're not running MPLS at all. So we have a tunnel running here, MPLS traffic engineering tunnels, because we're not doing segment routing traffic engineering today. So if I do a show MPLS interface, we can see that we don't have any interfaces there, and our forwarding table is still going to be pretty bare. So that's that. So we're going to go ahead and go back into config-T now. And there's a couple things we need to do here. So the first thing we want to do before we hop into the segment routing there is we want to go ahead and take a look at our segment routing MPLS. So the idea is that segment routing only affects the some labels in the requested SRV. Okay, I'll change that in a moment. The idea is that with SR, what we're saying is we're going to change how the control plane gets signaled, and then we're going to run MPLS. So the data plane is still MPLS. If the traffic goes out, we're still going to see an MPLS header there in between the layer 2 and the layer 3 headers. So the actual data transmission doesn't change between MPLS and segment routing. It's the control plane signaling, how we set up the MPLS core and the control plane that changes between SR and MPLS there. So this is saying that some labels in the requested sRGB range are currently in use. And that's because the idea with segment routing is that you have two label ranges. You have a local block and you have a global block. The local block is going to take on this MPLS label range command that I did. So it's going to go ahead and take on this MPLS label range, and that's going to be locally significant. So LDP labels are locally significant. These SRLB labels, your local block labels, are going to be locally significant too. But when you do segment routing for MPLS and you have an sRGB, most of your labels that you care about in this particular demo are going to be SR global block labels, meaning that they're not locally significant, they are globally significant. So that's the departure from LDP there. LDP had every single router generate a different label for all of the prefixes in the routing table. SR has the source of the prefix generate a label for it, and then that label gets pumped out to the entire topology there through the IGP. And what you're doing there is every single router is going to have the exact same label, which makes that label value segment more formally globally significant, meaning that it has to match. So that means that we have to make sure to have this work properly, that the range that we use for those global block labels is the same. Because the way that it gets advertised is that it doesn't actually advertise the segment itself. It advertises the offset of the segment. So it advertises the, the segment routing global block beginning range plus whatever makes a new label. So let's say we had a segment 16,011, and the global block is the default, which is 16,000 to 23,999. That's the default range of the global block. How it's going to advertise the segment is it's going to say, okay, the offset is 11. So it's going to be 16,000 plus 11 on all of the other routers, and that's how they're going to derive this label here, this segment value. Meaning that if you have a router here that doesn't match up its global block, it's going to generate a different label value, and that's going to cause problems. So that's a long-winded explanation for you need to keep the global block the same. Now, segment routing doesn't like that I have labels in the label table that are currently using that labels in that global range. It wants that label range to just be segment routing. So I'm going to go ahead and change the global block to, let's say, 40,000 to, we're going to change it to 69,999. And what I'm going to do is I'm going to go ahead and run that command. Actually, we're going to go into config-T, segment routing MPLS. Yep, that's that. And then I'm going to go ahead and run global block 40,000. 40,000 to 69,999. That's going to be my global block there. It's happy, it's enabled. So now what we're going to do is we are going to specify we're going to go ahead and configure the label here. So whereas LDP was going to manually generate the labels for us, segment routing requires us to generate our own segment values. It requires us to specify them ourselves. So what we're going to do is we're going to go into the connected prefix and map. SID meaning segment ID, that's the label value. And then we're going to go into address IPv4. And then here's where we're going to specify our label value. So the idea behind segment routing is that we are not going to generate segments for all of our prefixes. That's far too wasteful. So up here, we can notice that we have label values for /24s. These are our transit links and our /32s. We're just going to be generating label value for our /32s because the idea is that we don't want to waste our segments. We have a few of them, right? And we don't need these labels for these transit values because the idea is that the next hop in BGP for like an elder VPN is always going to be the loop back to that remote PE. So we're going to specify 22/22/22/22/32, and then we are going to specify, we can specify an absolute or we can specify an index. So the absolute is going to be specifying the whole SID value. The index is going to be an offset. It's going to actually be what's advertised. So we can go ahead and say that the index is, let's say, 11. And that's that. Actually, whoops, I didn't mean to do that. 21/21/21/32 index, and we'll call this 21. So that's that. And then what we're going to do is we're going to go ahead and specify router OSPF1, and we're going to go ahead and say second routing MPLS, and that's that. So that's all I have to do, enable it there. Second routing area 0. Oops, that's that. All right. So that's our configuration there. So same thing here, connect the prefix SID, map IPv4 unicast, and then we're going to specify the prefix, /32, index 11, and then router OSPF1, segment routing MPLS. And then connect the prefix SID map, address IPv4, and then 12/12/12//32, index gotta be 12, and then enable this in OSPF, segment routing MPLS. Same thing here, connect the prefix SID map, address IPv4, 13/13/13/32, index 13, and then we're gonna enable MPLS, segment routing MPLS under the IGP here. Connect the prefix SID map, address IPv4, 14/14/14, index 14. And then we're going to enable it under our IGP as well. And then 22/22/22/22/32, index 22 there. And then we're going to enable it under our segment routing MPLS. So that's the idea. So we go ahead and take a look at our MPLS forwarding table now. We can see that we have a bunch of new labels here. Because these are going to say merged. This is an artifact of the fact that I had LDP set before this and it didn't, and we're generating it for some of the same prefixes. And so we're merging it here, meaning that 21,000 is going to equate to the same thing that 40,011 did. But now we can see that we have the segment routing labels. Actually, I'm going to go ahead and do I and filter out for all the things that begin with 40. So this is going to be our segment routing labels here. And so the idea is that you can see that the labels are the same because we're swapping them out for the same thing. So let's look for 22/22/22/22, which is going to be the remote PE here. If we go ahead and do a trace route, all the labels you can see are going to be the exact same thing, right? 40,022, 40,022. Whereas in the case of LDP, that wasn't necessarily a guarantee because we had each router generating its own labels. Now that we're pushing out the labels centrally from the source of the prefix, the labels are going to be the exact same in the case of segment routing there. If we do a show IPLSPF database opaque area self-originate, we can see here that we have opaque type 4, which is going to be router information for the SID. And this is going to show that we have a, this end bit means no, then we have a prefix SID there. This SID is going to say 21. This is the offset, so every router down the line is going to take 40,000, which is the beginning of the global block range, is going to add 21 to it, and that's how it gets the SID. So LCF doesn't actually send the SID down, it sends the SID offset down, and then we just add that back into the global range in order to figure out what the actual label that we're using to send it is. But that's that. So if we go ahead and do a show MPLS-TE segment routing, SID database, I think that's what I'm looking for. Yep. We can see here that when we're doing the SID database, the codes, L means local, so this is the local SID that we're generating and pushing out, and then everything else we're learning from other routers. So we go ahead and go look at show MPLS forwarding table again, filter for whatever begins with 40. We're going to go ahead and run this command on all of the routers here. And so you can see that these are effectively one-for-one, except for where we have implicit nulls. So we have implicit nulls, then that doesn't really translate. But if it's not an implicit null, then the label value here is going to be the exact same thing going between each router. And we're not using LDP to do any of this. We're not using RSVP to do any of it. We're just using pure IGP, and then we're using IGP extensions for segment routing to support this. So you can do segment routing in OSPF, ISIS, or BGP. So those are your 3 routing protocols that have extensions that support the IGP stuff there. So that's that. That's all I have to show you. So we covered 5 things today. We covered synchronization, session protection, explicit-null, MPLS-TE, and then we covered segment routing. And we took a look at a sneak peek. So this isn't super deep. All these topics, pretty much, besides the first 2, maybe, go a lot deeper than this. Particularly segment routing, because you can do traffic engineering and all of that, and there's one for IPv6. But this is going to be the wrap up for the sneak peek here. I'm going to go ahead and stop the recording at this point because we're pretty much done now. Hopefully you guys enjoyed that. Hopefully it gave you a sneak peek as to some of the technologies that we can have there beyond just simple MPLS.